Okay, so then let's move to the visualization part. And in the visualization part, I'm going to start with telling you about a little bit of history and some conventions that are used in visualization, and then we'll actually go into the MolStar tool and see how to use it. So way back when Perutz and Kendrew, they were determining the structures of hemoglobin and myoglobin, they actually built physical models. So here is your wire model, and these are wooden models with slabs showing contours and so on and so forth. And something to think about, I find it really amazing, is that from these models, they were able to determine the coordinates that they submitted. Not exactly these, but these models, they built models that were the size of a whole room and so on. And then going from these physical models, there were scientists and illustrators who actually sort of took this information that is contained in that all atom model and distilled certain parts of the structure. So this is Irving Geiss's representation of myoglobin, where he's only showing the backbone atoms in this squiggly coil-like whatever. And then here in this disc-shaped representation, he's representing the heme group, and he's highlighting the two histidines that hold that heme group in place. And so this sort of representation allows the user, the viewer, to sort of understand what is going on in this molecule without getting overwhelmed by this huge, number of atoms and sticks and things. And so, and a similar kind of simplification was done by Jane Richardson. So she was sort of the inventor of this ribbon scheme. And here is a hand-drawn, painted representation of this triose phosphate isomerase. And again, we are looking at just the backbone that is represented in these stylized ribbons and arrows. And this gives you a sense of sort of the backbone architecture of that molecule without getting lost in the details of all the side chains and all the interactions. And this is where this idea of ribbons, so pretty much any visualization software that you pick has some rendition of this ribbons way of representing the molecule. And that gives you a certain kind of information. And so let's go to the next slide. And so inspired by these different ways of representation and the amazing graphics capabilities that we have now, we are able to display really large complex structures and color them in different ways and focus in and stylize different parts of the molecule to give different implications and ways of understanding that molecule or that assembly or that molecular story. So here, for example, we are looking at a wireframe representation. So this is much like what Kendrew was holding in his hand, the myoglobin structure. This is hemoglobin, of course. And here, every single atom is represented as a dot, and the covalent interactions are shown as a line connecting the covalently connected atoms. It looks quite busy. It's kind of hard to discern from this what is going on. So the simplification that the ribbons allows is that we take away the side chains. We're only looking at the backbone atoms. So it's the C alpha atoms connected to each other in this stylized ribbon representation. But now on top of that, color has been used to differentiate the 4 chains that make up this molecule. But what you have to keep in mind is that the limitation here is that you are getting this false sense of space here. It appears that these heme groups that are shown here are kind of floating in space, but actually if you fill in the side chains and look at the surface, you will see that these heme groups are sort of snugly fitting into these pockets where for each of these 4 protein chains. And so this surface and space filling view is giving you a different view or different understanding about this particular protein. Notice These two representations are representing all atoms. This is only showing the backbone and of course the ligands. And so the point in all this is that depending on the story that you are trying to tell, you may want to choose different representations to highlight whatever it is that you are trying to tell. And of course, for the molecule of the month figures, David is going to give you more instructions and guidelines on how he likes to present things. But if you're making scientific illustrations, so this is, for example, a figure made by a student many years ago. And the story here is how this particular protein, the Abel kinase, is able to bind two different drugs that go down two different pockets. And it is superimposed here to show that Gleevec goes down this way and Sprycel goes down that way. And this particular threonine interacts with both these drugs. And if this is mutated, both these drugs are unable to bind. And so this is the story that this student was trying to tell. And so using a combination of surface views, ball and stick, superimposed colors, all these things were used to tell the story. So again, depending on what story you are trying to tell, you probably will choose whatever representation is the best for that particular situation. Okay. Any questions before we jump into the MolStar tool? No? Okay. So in MolStar, what we are going to do is we are going to look at 4-HHP and try to do some selection and identification of what is going on around the heme groups. So let's get the structure up. So I'm going to go back to 4-HHP. And just clicking on this 3D view will open the MolStar page. So in the MolStar page, this is your 3D canvas. You can move the molecule here and navigate and click, and we'll look at that in a moment. On the top, this frame gives you the different contents of that particular, whatever you're seeing. So in this case, there are the two hemoglobin chains. So these are the two entities. And if I select one entity, there are two copies, so chain A, chain C. And then other than that, there is the heme group, phosphate, and waters. This panel is for you to be able to navigate and select and show different components. So for example, I can hide the polymer, show the polymer. Let's hide the waters for simplicity's sake. And I can just use the mouse in the 3D canvas to move things around. So everybody, I hope, is able to do this along with me. The question that we had set out to do is identify the histidine forming coordinate bonds with the heme group bound to chain A. List the residue number and chain ID. This is what we are trying to do. So we are trying to investigate the heme group bound to chain A. So this is heme group, the hemoglobin chain A, which is shown here. And the way I know that is as I am mousing over these residues, you see this is getting highlighted in the sequence panel, indicating this is the chain. If I mouse over this, this is a different chain. So here, the heme group here, I could just click on this, or I could find the heme groups here. Notice they are A, B, C, D, four heme groups are here. So I'm selecting chain A, and if I click on that, I get to explore the environment around the heme. So anybody unable to do this, please write in the chat box. And so once you're here, you can actually mouse over the residues shown and see this histidine, 87, is what we were looking for. This is forming a coordinate bond with the iron in the heme. And there's another histidine here, but that's the distal histidine. That's not what we are looking for. That's not coordinating the heme. So everybody with me so far? If you are, then the next question was identifying the histidine that is similarly bound in chain B. So I'm going to stop and I'll let you figure out what that histidine is. Okay. So this was chain A. I want you to check out chain B.
We already have some answers.
All right, so people are finding histidine 92, and let's see if I find the same. So the way I would go to chain B is I would just change this to chain B and click on that. And here we are, sorry. So this is the histidine we are looking for. And if I mouse over it, it is histidine 92 in chain B. So anybody who was not able to get to this point, or any questions or any concerns? No, okay. So the next question that your worksheet has is that in chain C, I want to look at what the C-terminal residue, this arginine 141, how is it interacting with whatever is in the neighborhood? And this is sort of an example of a situation when, let's say, you're looking at a particular protein where a specific amino acid has been described as being critical for either the function or the stability or something like that. Or there may be a situation where you're looking at a mutant and you're trying to understand how the interactions of that particular residue is different in the native versus mutant condition. So we want to look at a particular amino acid residue in a chain and see how it is interacting. And I'm going to let you take it on. So chain C, arginine 141. What is in the neighborhood? So I'll give you a minute to quickly get to that while I also try to get there. So the way I would go about this is I would go to chain C by selecting the entity 1 and chain C. So now I'm looking at chain C's sequence. If I click on this arginine, this purple colored arginine is the one in question. So notice this arginine is interacting with, let me just move this down. This aspartate in chain A, notice the description given at the bottom of the screen, this 3D canvas. It is interacting with some waters. It is also close to this particular tyrosine from chain B, but it's not a direct interaction. It is via this aspartate. And these interactions that we are looking at, so what is displayed here are just these hydrogen bonding interactions, but you can change the, so ionic interactions are not shown here, for example. So I turn that on and notice this arginine to aspartate, there is an ionic bond. And you can turn on and off these various options and play with it and see what you find. And when you are exploring your particular favorite structure for your molecule of the month feature or for your research and analysis, feel free to play with these options and see what kinds of interactions your particular residue or chain of interest is participating in. Okay. And the final part of this exercise was to superimpose the structure of myoglobin on hemoglobin. And the point here is to try and see how closely related or how similar the structures of these two proteins are, even though their sequences are not very similar and their function and behavior is really not similar. Myoglobin is a monomeric, it's happy to be a monomer. Hemoglobin is a tetramer. And so I don't know how many of you saw the comment that Stephen made that Irving Geist thought that hemoglobin was myoglobin times 4, but that's really not the case. But let's see how similar or different they are. So in order to do that, I don't know if I mentioned, there is a worksheet that goes along with this. So if you have not already done so, feel free in your Teams folder, there is a worksheet, you can download it. And so every single step that I'm doing, there are instructions in there. So feel free to play with it as you go along. But in the interest of time, I'm just going to show this to you. So in order to do the superposition, we will actually need to see this. I'm going to open another window. And we need to go to this link. So it's that same link without the 4-HHB. And it'll open this standalone viewer page. And in this viewer page, what we are going to do is we are going to bring in the two PDB IDs. One is 4-HHB, what we were looking at. And I happen to know that the myoglobin structure's PDB ID that I want to superimpose is 1MBO. So I'm going to add these two in here. So I don't have to download the file and put it in here. I can just say download structures, 4-HHB, and sorry, 4-HHB and 1MBO. Apply. So notice your 4-HHB is these darker colored chains that we've been looking at. And this light green chain is 1MBO, okay? Now, the instruction or the question says that superimpose chain D of the hemoglobin on the myoglobin. So I need to be able to select these chains. And so let's go back to this. And here, selection can be made by clicking this. So what we were doing previously, where we were focusing in on a particular residue or a particular ligand, we didn't need to activate the selection mode. We just could go and click on something, right? And it would show the environment around it. But now we want to select the whole chain. So I'm going to select the chain. I'm going to select chain D. So if I just click anywhere, it is selected. See, it's selected this whole chain. It's highlighted in green. And I'm going to now select the myoglobin. There is only one chain in myoglobin, so I can just click on this. Because the selection mode is chain, I click on anywhere in this chain, the whole chain gets selected. So now, right now, two chains are selected. And that's showing up here in the structure as in two structures, two chains selected. I'm going to say superposition by chain. These are the two chains I have selected, and I say superpose. And notice the green chain that was sitting here got moved if I remove selection. So the light green chain is sitting on top of this magenta chain. And the root mean square deviation of the C alphas in these two chains is 1.87. Okay. So if you look at it quickly, you can see that the myoglobin and hemoglobin chains are the overall structure is very similar, though there are subtle differences, and that's a whole other discussion. But to illustrate what the tool can do for you is it can take two different structures, chains that you specify, and it can superimpose them and allow you to then look at what is going on. And this may be a handy thing when you're looking at proteins that are either evolutionarily related, or proteins that are mutated, and you want to see how the structure is similar or different, etc. And to close, I wanted to finish up with a slightly different structure. And that is, since some of you are looking at nucleic acid structures, I wanted you to get a feel for how that shows up in MolStar. So the last part of the exercise was to look at a structure of a protein RNA complex. So this is ribosomal protein L11 in complex with RNA. The PDB ID is 1QA6. So Candace asks, what is the advantage of using a PDB MolStar versus a program like Primo? So the most obvious thing that I would say is that Primo is something that you have to install and put up on your computer and set it up and so on. MolStar is right here on the PDB website. You don't have to go anywhere, don't have to install anything. You just click on that 3D view button and you're right there. That is, I think, the most obvious advantage. But I think there are some advantages in many of these softwares that are, so there's Chimera, Pymol, people use different tools for different kinds of analysis. So if you are familiar with Pymol, feel free to use that for your explorations. This is just something that we are offering, and it's right here on the PDB website, and that's what we were trying to explain. Does that answer your question, Candice? Okay. I'm going to go to that last exercise, which is about 1QA6. And I'm going to just type in the PDB ID 1QA6 here. Oops, sorry. And here we are. So your protein is shown in purple, and the RNA is shown in this green colored ribbon-like thing, where each of the bases are shown as these steps in a ladder. And if I click on any of these, it zooms in and shows me all the hydrogen bonding, stacking, and other interactions. And similarly, if I click on any of the protein side chains, I can see how they are interacting, the protein RNA interactions and the protein-protein interactions and so on and so forth. This, I think the question asks you to look at serine 69. Because that was, determined to be a critical amino acid in the function of this particular protein. So if we go to the sequence and look at the ribosomal protein, serine 69 is this one, because I'm looking at 66 and so on. And if I look at the bottom here also, I'm sorry. Oh, you can actually expand this and look at it that way. I'm sorry, there are too many windows and boxes in my screen, so bear with me. So serine 69 is this serine. Notice it is forming hydrogen bonds with the backbone and making interactions with the sugar in the nucleic acid. And the backbone carbonyl is forming a hydrogen bond with a base. And so this particular, in the paper, this particular amino acid is described as an important critical amino acid for the function of the protein. So with that, I think that was all I wanted to share with you. Like I said, in the teams, in the general folder, the exercises, the slides, and the instructions for getting through these exercises is all included. So feel free to play with it. And I'm around if you have questions. I'm happy to answer questions.